Iron, mankind's most useful metal. The fourth most common element on Earth has been in use for 4,000 years, but it wasn't until the 15th century that furnaces were developed that could smelt iron in bulk. In the 18th and 19th centuries, there were numerous furnaces like these at the Blaenavon World Heritage Site in South Wales. They produced millions of tonnes of iron a year to fuel the Industrial Revolution and build a great empire. In a blast furnace, carbon in the coke fuel combines with oxygen in the air blast to produce carbon monoxide gas, leaving behind cast iron. At more than 1200 degrees centigrade, iron was run into a bed of sand in shape somewhat like a sow with piglets, giving rise to the name pig iron. When solid, these could be broken off and shipped around the country, indeed around the world, for remelting. Any shape could be formed in the sand floor of the casting shed and be filled with molten iron direct from the furnace, enabling very large castings to be produced. So the simplest way of using pig iron was by casting straight from the blast furnace. In the 1790s, John Wilkinson, a Shropshire ironmaster, developed a small furnace, a cupola, capable of remelting cast iron pigs. Cupolas were cheap and easy to use, and soon almost every self-respecting town in the land boasted its own foundry, producing a vast range of useful castings. The same process is still in use today. First, a wooden pattern is made, slightly oversized to allow for contraction. This can be used again and again, and of course, being timber, can be carved to any ornamental or decorative shape. A two-part frame called a moulding box is assembled. It's dusted with powdered chalk to prevent the pattern sticking, and covered with green sand. Traditionally, a natural mix of sand and clay was used slightly damp. This allows gases in the mould to escape and the casting to contract, yet gives a good surface finish. Rods are inserted to make runners for the metal to enter, and the sand tamped to an even consistency. The mould boxes are parted and the pattern removed. Nowadays, heat-curing resins are used to improve mould strength and surface finish. Solvents are flamed off to speed curing. The mould halves are reassembled and weighted to prevent the molten metal floating the top box off. Meanwhile, in an electric, oil or gas-fired cupola furnace, pig iron is melted, ready for carrying to the mould. A spatula holds floating dross back in the ladle. When the casting has cooled, it's broken out of the mould. The iron leaks slightly where the mould boxes meet. This flashing is dressed off, together with other defects during the fettling process. The third traditional way of using pig iron was to convert it into wrought iron using the puddling furnace. The most efficient process was developed by Henry Cort in 1784. Here, the cast iron is heated in a chamber away from the coal fire to avoid contamination. The fire's heat is reflected off the roof, so this is called a reverberatory furnace. Oxygen in the air passing through the furnace combines with the carbon in the cast iron, reducing it to almost pure iron. It's stirred to ensure even heating, and as it becomes hotter, it's worked or puddled, then divided into 50-kilogram balls. Shingling under a large power hammer expels slag and consolidates the spongy mass into a solid billet. While still hot, this was repeatedly rolled to consolidate it further. It was then cut up, reheated and re-shingled. It was rolled again and may go through the whole process several more times, its purity and strength being improved each time it's worked or wrought. Grades range from basic crown or merchant bar through best to triple best for highly stressed applications. The last puddling furnace stopped work in the 1970s, but recycled wrought iron is still available. Then in 1856, while searching for a faster way of making wrought iron, Henry Bessemer discovered instead a quick method for making another material: steel. He blasted air through molten pig iron via holes in the base of his converter. Oxygen in the air drew out some of the carbon, as in wrought iron production, but the remaining carbon combined with the iron, making a material with very different properties. Steel was stronger, tougher and more uniform than wrought iron, and could now be made in much bigger cast or rolled sections. It was discovered the process produced its own heat, so no fuel was needed. And the converter could produce in half an hour what a puddling furnace took a week to make. The cost of steel therefore fell dramatically towards the end of the century, and the fate of wrought iron was sealed forever.
If you take a piece of modern steel and break it, you see a fine granular structure. Traditional wrought or puddled iron is more ductile, that is, it's easier to bend, and has a strong wood-like grain. This test was in fact specified under the British standard BS 51 as a test for quality. The iron had to bend to the same diameter as the thickness of the bar without breaking. Wrought iron was shaped by the blacksmith by drawing down, that is, reducing the width by hammering, upsetting, that is, hitting the end to make it larger, punching to produce holes, using swages to make preformed shapes, and various other techniques to keep the grain intact for maximum strength. Joints were made by collars, which clamped the metal together, or rivets, which produce very tight joints that will keep out the water, or by fire welding, that is, heating to white heat and forging together. Steel doesn't have the same properties, so it can't produce shapes of quite the same delicacy. By contrast, if you break cast iron, it's brittle and has a fine grey granular structure. It's made from wooden patterns, so they can be carved to any shape to incorporate any amount of decoration, and parts can be made to slot or dovetail together, and any number of similar castings can be run off from one pattern. Holes can be cast in for bolts, or cast iron can be drilled quite easily because it contains free carbon, which helps the helps to lubricate the machining process. So nature's provided us with two forms of iron with complementary properties. Wrought iron's ductile, it can be formed into slender shapes, good in tension. Cast iron is naturally decorative, corrosion resistant, and good in compression. And you'll often find the two of them used together to great effect in buildings and engineering structures.
The explosive development of the railways in the 1840s brought cheap travel for the masses and a demand for leisure facilities, like seaside piers, of which more than 50 were built in English resorts. Corrosion-resistant cast-iron columns braced with wrought-iron tension rods provided strong, elegant structures, and most are still in use today. A 1,000 bridges a year were being built in the mid-19th century, many of them in iron. New forms of construction brought ever bigger spans. In Bristol in 1831, Brunel won the competition to bridge the Clifton Gorge with his suspension chain design. A clear span of 214 metres, 75 metres above the River Avon. A cable was first slung across the gorge to carry men and materials, and when a lack of funds delayed construction, people paid to cross the adventurous way. The cable was simply a 45mm diameter bar of wrought iron made from short lengths, fire welded together. These samples of the same material, welded up at Dorothea Restoration's workshops, are being tested to destruction at the University of the West of England. So how strong were the welds? Each bar broke at a stress of around 18 tons per square inch, at least 80% of the original bar strength. This would have given a safety factor of about 5, so the intrepid travellers were actually quite safe. Eventually, the Clifton Bridge was built with chains from Brunel's Hungerford Bridge in London. Again, fire welds were used to join the rounded heads onto each of the 4,200 links. The original wrought iron chains and hangers still carry road traffic today. The care and conservation of iron is a complex process, and establishing the true extent of the suspected problem is a vital first step. We need to know what loads the structure has to carry, how its components support these loads, and the condition of each part. Rust occupies more space than the iron that produced it, so it may be necessary to cut out a section to find what thickness of metal is left. Be aware of areas you can't see. Flanged beams may appear sound from below, but a build-up of rust on the upper face can cause cracking which is not initially visible and only shows when the flange shears. Columns are another possible source of hidden problems. Wall thickness may be uneven if the mould core distorted during casting, and if used as rainwater pipes, they can block, then freeze and split. Water entering joints often causes rusting. Rust expands and over time can split cast iron sockets. So paint should be removed in critical areas to allow inspection for cracks. Minimal intrusion and loss of evidence are the fundamentals of conservation. Repair should be preferred to renewal, carried out with traditional materials and techniques. New materials should be distinguishable from old on completion, and reversible processes used wherever possible. As demand on our historic structures increase, they should be protected from accident or abuse. On this bridge in Bath, vehicles are kept away from the early parapet by a substantial new cast iron curb. Original material can often be retained by hidden strengthening, as on this parapet in Bristol, reinforced with steel sections hidden inside the cast iron. Cast iron, being brittle, should always be repaired by cold processes if possible. It may be feasible to drill broken components and thread the holes. They can then be screwed back together on studding, bedded on a suitable mastic to keep out water. Remedial work should generally be completed before painting so that the paint coat subsequently seals the repairs. Any stainless steel bolts or plates must be insulated from the iron. There is electrolytic action between the different metals, which increases with pollutants like salt. Cast and wrought iron are both sacrificial to stainless steel and will corrode away in damp conditions. Another cold repair process is stitching. A hole is drilled into the crack and a small jig pegged in place. A series of holes is drilled into the casting, stopping just short of the far side. A pneumatic chisel is used to take out the webs between the holes. Then a steel lock or stitch is driven in to hold the two parts together. More stitches are added as necessary to fill up the full depth of the casting. Holes are then drilled along the crack and overlapping bolts screwed in to provide a seal and prevent the broken sections sliding out of alignment. Finally, the protruding parts of the bolts are cut off and all is dressed tight. The result is a permanent watertight repair without the use of heat or sealants that can be carried out on site with portable pneumatic equipment. If a casting is incomplete, a make-up piece can be copied by a simple process. On this Victorian drinking fountain, a corner scroll is being reproduced. The first step is to apply a latex moulding rubber. Plaster of Paris is poured into the latex mould to create a pattern. This is then painted, taken to the foundry, and used to make a new iron casting. The new casting may need dressing to remove the flashing line caused by slight leakage of metal between the mould boxes. It can be bolted, stitched or welded in place. Electric arc welding is fast but recommended only for non-structural parts. The very high temperature of the electric arc tends to shock and crack brittle cast iron around the weld. The whole area should therefore be preheated gently and the new piece secured by intermittent welds. The minimal amount of welding should be used on non-structural repairs, gaps being made good by a 2-pack resin. For cast iron, gas welding is better than arc welding, particularly on thin sections. The flame temperature is much lower than that of an electric arc and the metal is heated more slowly. Casting should be heated slowly before arc welding, then cooled slowly afterwards if cracking is to be avoided. Small parts can be heated with a gas torch, but a special furnace may be needed to control the heating and cooling of large castings. On the whole, therefore, it's better to repair castings by bolts, plates or stitches wherever possible, rather than subject them to the stress of heating. Umberley Bridge in Devon, with its decorative cast iron parapet, was originally built in Victorian times to carry rather less traffic than it does now. Damage caused by a farm trailer was repaired by casting new panels to match the originals. The original grey or flake grade of cast iron was used, but a stronger, more ductile grade of iron called spheroidal graphite is also available for highly stressed applications. The original smashed components were retrieved from the river and welded back together to form patterns for the foundry. Traditionally, green sand, a natural material, was used to form the moulds. When damp, it would hold its shape. Dry sand mixed with calcium silicate and then hardened by injecting carbon dioxide is a modern equivalent. Although jobbing foundries are becoming rarer as the industry gradually moves towards mass production techniques, the skills of the pattern maker, moulder, foundryman and fettler are still practiced today and have hardly changed over the last 200 years. These gates from an historic building on the south coast have been exposed to seawater for nearly 100 years. Decorative wrought ironwork often looks at first glance worse than it really is. This is because rust expands, so the volume of rust is greater than the amount of original metal affected. Wrought ironwork was so called because it was wrought or worked, and designs were developed that made best use of the ductility and malleability of the traditional material. When making replacements for traditional wrought ironwork, the correct material and blacksmithing techniques must be used to achieve the same fineness of detail. The blacksmith makes many of his own tools, especially in refurbishment work. Scroll formers, bending irons and other tooling has to be made to fit original components so that they can be replicated accurately. Recycled wrought iron is still available in a range of plain sections for restoration work. Water leaves are a traditional form of decoration that come in many shapes and sizes. If an existing leaf needs to be replicated, its unbent profile can be found by means of a piece of card and then marked onto a new piece of wrought iron sheet. Again, a special piece of tooling has been made to support the leaf during forging. Yet another specially made tool is used for crinkling the leaf. Rusted areas can often be reclaimed by a small localised repair. The aim is to retain as much of the original material as possible. This component is being repaired in situ with a wrought iron patch. Because the sections are thin, they're being gas welded or brazed rather than arc welded. A special rod of bronze is used to fill the joint and fuse the two parts together. These components are being made by incising and chasing the iron, while supported on a lead or pitch block. This high-quality ornamental work came into vogue in England at the end of the 17th century, following Jean Tijoux' famous work at Hampton Court for William and Mary. The creativity and skill of the blacksmiths was pushed to new heights as the nobility and gentry commissioned grand gates, screens, fences and other ironwork for their estates. Where the sheet is embossed from the rear, the technique is termed repoussé. Quality ironwork must be treated with great care when being cleaned. These gates from Chirk Castle have been flame cleaned using an oxypropane torch to remove the many layers of old paint. They're wire brushed and then hand painted with several coats of lead paint. This can only be used on Grade 1 listed buildings with the written approval of English Heritage. Rivets are the strongest and most durable traditional method of joining structural wrought iron components. The quickest method of removing them without damaging the original plates is by slicing off their heads, a process called rivet busting.
Almost complete thickness of metal here, despite the appearance of the troughing nearby. The water running through here, which is clearly what's caused the problem in this area. But the concrete itself is actually in very good order. This is one of the drains to take water from the edge of the road, drop it straight in the river. Unfortunately, it's rather near the edge of this flange, so it's been dropping water onto the flange of the longitudinal beam, which has caused quite extensive rusting down here. And also, I think that probably a leak around the drain has caused moisture to be trapped up under here. And the rusting caused by water running down the side of the beam has actually caused it to rust right through at this point.
Cookham Bridge was built in 1867 and is listed Grade 2. It's carried traffic over the Thames near Maidenhead for more than 130 years, but was closed for just 4 months to allow major repairs. The structure is a series of cast iron trestles spanned by wrought iron beams and corrugated plates covered with reinforced concrete. The first task was to remove all the concrete to allow full inspection of the ironwork. An early decision was made to adopt strict conservation principles and retain as much of the original metal as possible. The thickness of every plate was checked and the wrought iron spans modelled by computer to enable the engineers to determine which wasted areas could be tolerated and which had to be patched. Corroded areas were cut back to sound metal and plates cut to fit each hole accurately. New steel plates were first tacked in place and then welded round by the MIG process, where the metal is melted locally by means of a continuous electric spark protected by a shield of argon gas at the torch. This produces a molten pool where the plates fuse together. The plates of the main span were just 6 mm thick, so a full depth weld from both sides was essential. Wrought iron is fibrous and contains small natural faults. The contraction of the hot weld often pulls the fibres apart, so it's important to test structural repairs for cracks. One very effective method is to spray on a white powder, attach a magnet, and then apply magnetic ink. Cracks are ground out, re-welded, and retested. The concrete deck is supported by corrugated troughs, again repaired by electric arc welding as necessary. Modern traffic puts a greater load on Cookham Bridge than it was originally designed to carry, so an unobtrusive method had to be devised to strengthen the roadway. Computer modelling proved that the most effective and least visible method was to make the troughing and roadway act as a single composite beam. This was achieved by fixing the ribs and deck plates together with a large number of bolts. The projecting bolts were cast into the reinforced concrete slab to act as shear studs. This tied the whole structure together as one very strong composite span. The plates, angles and tees of wrought iron structures were usually fixed together by rivets, always set red hot. As the rivet is hammered up, it spreads to fill its hole, locating the plates so that they cannot slide. When the rivet cools, it shrinks, pulling the plates together and producing a very strong and durable joint. To comply with conservation principles, riveting should never be replaced by welding on historic structures. Whether wrought iron or cast, functional or decorative, the aim in the repair of all historic ironwork is to retain as much of the original material as possible and stabilise its condition in accordance with sound conservation principles for the benefit of our successors.